Thank you for coming. I know it's a lunch hour, but you all still did, some of you all might have skipped your lunch. And I'm really grateful that you all are here. And hopefully, you all get something out from this presentation. We'll get going. Quick intro, Vikas Venavalli. I'm a lead ML engineer at Starbucks. I've been through this ML journey since like quite a few years now. Prior to that, I was more into engineering. And the way I got into this ML engineering was like more than a decade ago. One of my friends who works at Starbucks too is actually sitting over here. He takes me into this room, and he shows me this fancy model that he built. But the first thing that stood out for me was not the model, but his server that was running under his desk. Right? The model, actually, when he did the demo, it was pretty cool. But I was always like looking at the server, I was thinking like, how does this work? Like he's running the model, he's getting these predictions, and what is he going to do with it? But eventually, right? But the modeling part kind of interested me. I eventually got into it, and then I kind of, moved to different teams, and I got the opportunity. I was very fortunate about it. So fast forward, like Starbucks, right? We moved away from running our models under our desks. And then eventually, we started using Databricks primarily for a compute. And one of the main things that I want to highlight is most of the things that we put in place was based on our personal experiences. It's not like we had a big picture before we implemented the solution. It's just like we kind of organically grew into this. And one more thing I just want to highlight is as part of this journey, obviously there were quite a few ups and downs. The adoption rates were also weren't that great at times. But eventually, in the end, it worked out. And hopefully, I'll go through some of the things that we have in place. And maybe it might also help you all from using some of these components that we have. So basically, the introduction, what is DeepBrew? I'll give some of our principal objectives. I'll try to tie it to our problems that we have and how we kind of relate it to our objectives. And in the end, we'll try to stitch them together, and hopefully it makes sense. The overall platform architecture and some of the pipelines, some of the basic things that many of you all already know. And some of the interesting things would be like, how do we expose model as a service or data as a service? We'll go through that too. One big thing, at least like if you all are not already doing the environment setup when we get there, that is something that I personally like. And let's get going. Yeah. So what is DeepBrew? It's our AI/ML platform. One of the main reasons why is we want to uniform the way things are done at Starbucks. Because Starbucks has like a huge team of data scientists and engineers. And we see like some of the teams, they're very like domain specific. And some teams tend to follow some really great practices, whereas other teams kind of struggle. So we wanted to unify the way how things are done across Starbucks. And in the end, there are like quite a few advantages, because obviously everybody knows the churn ratio. You'll have like really good data scientists, engineers. At some point of time, they're going to leave. And then again, some part of the stack is going to be way ahead than the rest of your stack. So that was like one of the primary goals too, and obviously scaling, and we'll get to that part. So these are like some of our principal objectives. I know like some very cliche statements over here, but it kind of makes sense when you think about it. One of our main problem is like some of our customer-facing models. We expose those models to our customers directly through some kind of recommendations. It could be like drive-through or through a mobile app. And many of our obviously our data scientists, they come from like strong math background, and they somehow hack their way and like they build APIs, and we try to expose them. We barely get them up and running. Right? And it takes time. Like they get the model ready pretty quick, but the productionization part, it tends to take a lot of time. And even if you productionize, by the time you're not really thinking like, how do I, again, take the data back, maybe reuse it for retraining purposes. And by the time we have this set up, like, it probably takes like a couple or more months, right? So the bigger thing is like when we are deploying these APIs, one of the main challenges was scaling. Initially, we started with using some very like basic VMs because that was the easiest to do. And then Azure came up with web app services. There were some limitations, but they were all discoveries. So we always had a challenge of like, how do we scale all of them for the amount of requests that we get in a single day? Like I said, right, the collaboration across different orgs, like org A does completely different from org B, and like because org A supports a different domain from the other org, and like if a data scientist moves from one org to another org, they have to again relearn the entire thing, and the way you manage your code is also different. The way you structure it, some of the good practices that you follow is not consistent across the organization. One major thing is like some of the model management, feature management, or the way we were managing it across the orgs wasn't consistent. Like some of us were like building these models and they store it in an ADLS location. The others were like pushing it to a database. Like we were kind of like we are still, I wouldn't say like we have like completely moved on. Like there are some places we are still doing it. But we're trying to like have some consistency, like how we manage our models, features, and obviously our data sets too. In the past, what used to happen is like a data scientist, and also some of engineers, they would build these really fancy models because they're really excited of it. We schedule them, and then when the next project comes, we've forgotten that we have scheduled a model which is running on a regular basis. And when it fails, like everybody is busy. You get that email, and nobody is looking at those emails at the point of time, and we tend to miss some of those emails. So there's like, how do we like set up a framework so that we could have another team which can support it? But they'll be only able to support if there's like one way of doing it, right? Like if I had anybody from Starbucks, right, they would be rolling their eyes because in general, like Starbucks doesn't like just one way of doing it. We want to be as flexible as possible. But in the end, it is like when you have an organization of over 300 engineers and scientists, like having a consistent way of doing will also help us to quickly transition all your work to an operations team too. Right, like this is like very basic overview. I just want to give like basic overview of like what it is, and then we'll go into the details at each point, and hopefully I can add some value over there. So EDAP is like an enterprise data analytics platform. That's what we call. That's where all our enterprise data sets reside. The way we create our enterprise data sets is like we have like a governance team. Usually we work with them before we create these data sets, and we have quite a few data engineers who tend to create those data sets, and they stage it in Azure Data Lake storage. And as part of that, the way we have set up this EDAP system is like it's based on domain subdomain model. So and based on your domain subdomain model, like we have managed the permissions, and also like when it's like very PII sensitive, like we've added some elevated permissions to it. So this is the way like we have been managing that enterprise data sets. But as part of your like machine learning lifecycle, for example, you're building a model. Then the data that you're reading may not always be as part of EDAP. You could be reading it from multiple sources. And to find a data engineer, and obviously that could potentially take time. So some of the data sets are again like are managed and created by data scientists or ML engineers. But that is part of the life cycle. And the thing is like obviously this is like some of the standard things where our training happens on the Databricks compute. And as part of the training part, some of the things that we want to like keep in mind is like after the training is done, obviously everybody cares about the inference or the prediction part. And as part of the inference or the prediction, what we have, like obviously, like in many cases, it's batch, right? Like 95% of the cases, we do batch inference because we are forecasting. That's like a major chunk of it. We use the batch way of doing it, but only the consumer-facing are the ones we kind of do it like almost real time. But once the models are trained and registered, we have a process where we take those models and deploy it. The good thing is like MLflow was like kind of a blessing. So we have started managing these models in a certain way. And then based on if it's a batch prediction or if it's like online inference, we have different paradigms. And one thing we'll get to that microservices architecture as part of the future slides. Like based on the type of inference, we give like different ways where the data scientists can pick and choose like how do they want to expose the models or how do they want to expose the results basically. The auditability, I mean, this is something standard, like obviously Starbucks really cares about it. So at every point of time, we log all the events to a centralized location, and that is actually managed. And we have a GCS team which kind of looks at all the information carefully. And if it's something out of the anomaly, they tend to point it out to us. And another big thing is obviously the usage of your compute. Because since many of them are like so strong from the math background, sometimes to solve the problem, like we throw in like really big clusters, but we don't really see that we're not utilizing it completely. So like that kind of information, like we kind of like push it to a centralized location, and then we have dashboards, and we have some kind of alerting that goes back. It sends email to the owners of those jobs. So this way, like they are aware that the resources that they have, like they're using it about like 50% to the capacity or maybe like 80% of the capacity. This is like a very basic overview. So we train, we hit EDAP, we read the data, obviously we build features, we train it, and there's some kind of evaluation going on. And once it meets certain criteria, then we figure out like what is the best way to deploy it, whether it's batch prediction or online. So these are, and if it's online inference, we have, or batch inference, we have 3 paradigms where it's like a model as a service, function as a service, or data as a service. We'll get to that. And also your batch predictions can be exposed via mounts to other teams if they want to use like a SQL type of query layer instead of the API type of the query layer. Right, so this is like, if I break this down, like I've kind of grouped it into different groups. The first one would be basic training pipelines, and we'll go through it. Obviously, there are multiple sources. Azure Data Lake Storage is like the most, that's where most of our enterprise data resides. For near real-time type of data, we use event hubs, and we have this event streaming jobs running in Databricks. For blob storage, what we do is for retraining purposes. For example, when we expose an API to a customer, so we want to track what the request was and the response, just so that we can reuse the data for retraining. So that kind of information goes into the blob storage. We'll get to that part. The main thing is the orchestrator. For most of the use cases, we use Databricks, and that's our recommendation to use for the orchestration needs. But again, there are like some complex orchestration needs where like using Databricks may or may not be possible. That's when we use Azure Data Factory. We are also like looking into managed Airflow, because that's one thing we want to get away, like having like a dedicated platform team to manage these components. So that's why like our goal is to use most of these Azure components that we're getting out of the box. So this part, like I think we're already familiar, where we have these Databricks notebooks. Using that, we are like ingesting data. It could be from multiple sources. And as part of ingestion, there is some like data transformation, cleansing. We're building features. We're registering features to the table. We are registering those features. So and the full transparency, right? Like we are at a place where like few of us are registering the features into the feature tables, and others are still persisting the features in like just like a Delta format. But again, right, our goal is to like like organically grow like where we want to be, rather than like trying to make like one huge shift. But we are getting there, right? So once our features are created, obviously like pretty obvious things where you're training the models, and we're registering the models into MLflow. The goal is to have like one centralized model registry for the entire enterprise. And as part of the registration, we ensure that there's proper tagging. Like MLflow comes with its own way of versioning, and that's like incremental. But we want to tag your GitHub version of the code to the model, so we know that that version of the code is actually used for your model training. And obviously, we understand that you can take the files and you can also register to MLflow at this point. But you might end up having a lot of files being attached to a specific model. So basically, we use MLflow to track the models. And as part of that, we insist that we add additional tagging to it, to track the cost, to track what version of code was used to generate that model. And primarily, we want to expose this layer for the rest of the enterprise so that there's like one-stop shop for all our modeling needs. So that's basically our model registry. And eventually, the feature registry also, like we're going to take the same approach. One thing on the right-hand side, if you see, like we have Redis, Cosmos DB, and SQL Server. It's mainly for online inference use cases. Some of the features need to be persisted. So it depends on the size of the data. For example, if the size of the data is around like 10 terabytes, then we don't put it into Redis. Redis is kind of expensive. So it's based on the use cases, like what should be our request response time. For example, Redis gives you latency would be around like 6 to 12 milliseconds on average. For reading those features, just imagine having an API, and if it has to like make multiple requests to your data sources, and if it's a little bit complex, then hitting like a SQL Server, Cosmos DB, they give you good throughput, but it's definitely not going to beat that 6 to 12 milliseconds, right? For really large data sets, we use the Postgres Cosmos DB, and it's working really well for us. Like we've been loading like 10 terabytes of data under like about like under hour and a half. And this is just for like one specific use case, right? Like, and we have multiple use cases. So from that perspective, like we were able to like set this up in such a way that like your reads, your writing of your features or your batch predictions into some of those data stores are kind of seamless. The SQL Server, like we do use it. I mean, if some of the folks are more familiar with that database, we just keep it open so that the data scientists are comfortable based on what their needs are. This is like the basic overview where like we use an orchestrator to orchestrate all of these. Most of the machine learning pipelines are like a little bit simpler, but there are a few that get complicated. So the complicated ones are the ones where we use Azure Data Factory. And I'll come to the part where to set all these up from a data scientist perspective, it could be a little bit overwhelming. But what we have done to simplify some of these integrations, I'll get to that part. So once, let's say like in the previous stage, like for example, I have registered all my models into MLflow based on different data sources. The features that I needed for online inference has been pushed to Redis, Cosmos DB, or SQL Server based on use cases. And if it's a batch inference, and if you just need like, if you're going to be using a SQL layer to extract the data, we just write it to ADLS for your batch inference. So this part I think is pretty straightforward. The next thing is once your models are registered in MLflow, that for online inference, one of the things is like how do we expose it as REST APIs? I mean, Databricks now has a way to do it. But when we started, we weren't really sure like exactly how we're going to expose this as REST APIs. So we have our own process where once your code is checked in, we have an ADO which gets kicked, which takes the code from GitHub, and then eventually it's going to read that specific MLflow version of the model. It packages them, and obviously it builds some wheel files or jar files, because in most cases we support both Python and as well as Java too. And then we register your images into a container registry and the standard, right? Then we take those images, deploy into AKS, and that's how you get the scaling. But one thing is like once you deploy your models as REST APIs in your AKS, we use APIM for exposing them to the internet, for example. And even also as part of it, let's say if your AKS system is down, we still don't want to give server down kind of messages. So we provide some kind of default, the default response or the default predictions we kind of manage in the APIM layer too. And also like some of the timeouts, like sometimes these models, because we have some kind of a concept called online inference, where we deploy the model as an API. In other cases, we take all the predictions, put it in a database, so that our request, so that we are able to read those predictions within 60 milliseconds or 80 milliseconds, right? So it depends on a use case. We pick and choose which paradigm to go to, but in all these cases, at times there could be latencies with the database. There could be failures around your network, and if I'm using an app, for example, if our customers are using our app, we don't want them to wait for a really long time. So those kind of timeouts, we have put them in APIM, and as part of the APIM for every API or all the models that we have, we set these timeouts and a default prediction. So this way, at all times, we are always providing you some prediction or the other. In cases where the SLAs are going to 300 milliseconds, we just give a default predictions for in those cases, right? And once you see as web service, this is part of a DeepBrew 1.0 setup. Basically, we use it for A/B testing, some kind of routing needs where we have a champion challenger model. Based on certain configurations, we kind of route the traffic to different models in the backend, right? So the thing is, we have 3 paradigms, right? Model as a service, function as a service, and data as a service. I'll start with function as a service. So basically, all your modeling all the time doesn't mean that it's going to have a serialized model. Some of the ML engineers and the data scientists, they're really good with Python. So what we tell them is you write a Python function with all your functionality. It could be where you can call, where it could be a complex Python application itself. But your goal is to have a function, and you write all your logic in it, and then commit it to GitHub. Once you commit it to GitHub, the CI/CD pipelines are going to kick off, and they will be exposed as REST APIs, right? That is our function as a service. So our engineers don't need to know anything about the API, but more about focus on what you're really good at, write the functions, and then we'll take care of the rest, right? The second is the model as a service. That is basically all you care about is registering the model to MLflow, and then the pipelines kick in, and they'll automatically expose them as REST APIs. One of the question could be, okay, you're building these services, and the services get deployed in the AKS layer. How about the scaling? So when the CI/CD pipelines kick in and we package them and we deploy them to the AKS, basically what we do is, if you're familiar with Helm charts, some of the Helm charts are generated based on some very default configuration. But obviously, there is going to be some kind of load testing going on before we deploy. And that is where we kind of ensure that your AKS cluster is rightly sized. But at the end of the day, from a data scientist or from any other engineer's perspective, they don't need to worry about any of these orchestration needs when it comes to your AKS layer or further up, right? Basically, just focus on your core problem. That would be how do I build good predictions, right? And that is where we want them to end. And then the onus is on automation process, which will kick in and will take care of the rest. Yeah, one thing is, as part of this function as a service and model as a service, we also give some kind of functionality where for caching needs, for example, I understand Python gives you some level of caching annotations, But as part of this framework, we have these custom libraries, which will enable you to send data to any of the caching data stores just by annotation saying that I need this data to go to this location. And it takes care of the caching where either it can cache the data locally or it can cache the data in Redis too, because Redis is always available. So some of your caching needs is also set up as part of this framework. Well, one more important thing is logging, right? Like how do you manage the logs? What is observability? Right from the data pipelines or your machine learning pipelines that you build, and then once you have trained the model, you have registered it, all those logs, then the next step would be I'm exposing this model as a REST API. How do we track all those logs? And then what do we do with those logs? How alerting needs to be set up, right? And all of these kind of come into play too. So we primarily are using Datadog. But another thing is, as part of the logging, we want to use some of the logs for retraining. Initially, we started pushing all the logs to the Datadog, but at some point of time, but for retraining purpose, again, we had to call the Datadog APIs and then retrain it. So we took slightly different approach. We're using vector agent. Basically, it's we do what basically it does is any of the standard Python logging, it goes to the vector agent, and as part of your logging statement, you just tell, hey, send these logs to Datadog, or you send these logs to a blob storage. If you need it for retraining, you just add the flag, send it to blob storage, and the vector agent takes care of it behind the scenes, and then the data can again be reused for your retraining purposes. And obviously, the standard, once you have data in Datadog, we are integrated with ServiceNow, and that's where your alerting comes into place. Right? This is so what I've shown, right, I'm trying to rush since we have only 40 minutes or so. So now we are kind of have some kind of bare idea, you have the model training pipelines, and then we spoke briefly about the inference styles, the different inference styles, and the third part is how do I log some of the information and how do I generate alerts. But the bigger thing what we've noticed is how do we effectively manage environments? Because if you look at the notebook code, sometimes what happens is we create tables and we say and we tag underscore prod or underscore QA, right? So your environment code is tightly integrated with your machine learning pipeline code, right? So if you have one mistake somewhere where you're looking at, if you haven't updated your parameters correctly, it will start reading data from a wrong data source, right? So in that way, what we have said is all your development can be done in your experimental environment. Don't worry about creating data sets which says underscore prod or underscore QA, but be consistent with the naming. And we try to replicate the same thing in all the environments. So you have different Databricks workspaces, basically. Every team gets their own workspace, and we have CI/CD pipelines in place. And once they're ready with the code, basically they trigger those CI/CD pipelines, and when they deploy, we ensure that the same structure that they need in the lower environments is also available in the higher environments. But one thing to keep in mind is there should be a standard way of doing things, right? If you don't have a standard way, then you cannot build all of these tooling in place. So what we do is we provide these cookie cutter templates. Basically, what the cookie cutter templates, the way to set up is either for a data scientist, they can go into the Databricks environment and say cookie cutter, and if they type in cookie cutter, it gives you a bunch of options asking them some values, asking them what is the model framework they want to use, or what is the name of the model, some very basic questions, and based on that, it creates a repository for them. And also it takes the repository and integrates with Git, and it sets the end-to-end up. So as part of the cookie cutter template, basically what they have is a sample code to manage all their ML engineering or the data science needs with sample code. So that includes like, how do I register to MLflow? How do I register these values into features? For this project, where do I need to write the data? That's a big question, right? In ADLS, you could be writing in multiple different places. So as per the cookie cutter template, we set all those defaults. So basically, our data scientists, all they do is they go to one place, and then basically they use their own algorithm instead of the default algorithm that we provide. And also the data sources, right? Like you could be potentially reading the data from different sources. So once they have this cookie cutter template, and if they use the cookie cutter template to build their models automatically with all the sample code is already provided in it, then it becomes easier for us to use our existing pipelines to move to staging a pre-prod, right? Like when we take this data, take this repo, when we deploy, we execute it end to end, and most cases it works, right? If it doesn't work, that's when we see like, did our data scientists, engineers do something manually to get it running? Technically, there shouldn't be any case where they have to like manually add some kind of environment variables or values to get it running. So that will be like a good check for them. And many times the way it works is, at least like in our organization, we are just experimenting it, and many of us don't want to productionize it, like true productionization. So in those cases, like we take the code, deploy it into staging or pre-prod, and we leave it over there. And if we think that there's a strong business use case that this needs to be monitored 24/7, and we take the same setup and we migrated it to other environments. So that is where like our cookie cutter templates come into play, and it kind of helps us out to like standardize one way to register your features, one way to have like standard naming conventions, one standard way for your configuration management. For example, we use Dynaconf. So like, how do you manage your configuration parameters? So there's consistency across, and it's easy. Like, if you know one way to do it, then it's easy to like go through multiple repos and figure out very quickly like how things are actually being done. And these are some of like some of the ancillary highlights that we do, that we get as part of this setup. Hey, bring your own model. You can bring like third-party models, and then you could still register to MLflow, and automatically, they are exposed either as APIs or they can be used for your batch predictions. I'll probably give like last 5 minutes for questions, so I'm going to just run through it. This is like some of the current work that we're currently doing. Obviously, LLM is like the new thing. I wouldn't say new, but there are a lot of use cases for LLM, so we are also exploring it. The GraphQL API and federation, because currently we use REST APIs for model as a service, or data as a service, a function as a service, right? Like we want to have like a unified GraphQL layer, so that would probably standardize some of the things. Enterprise feature store is something we're working on. Service mesh, we definitely want to invest in service mesh. It helps us with a lot of things. For example, it'll help us route some of our production traffic to non-prod environments. So this way, we can use some of that data for training purposes, and obviously champion, challenger, or A/B testing, or any of those. And the last is the AI governance. It's like, it's been going forever. I don't think we have completely solved it, but we're trying to figure out, we're trying to evolve, like wherever the industry takes us, right? That is the direction we're going to be heading. So basically, whatever I said, right? Like some of the things that we're doing by standardizing some of those practices with the existing frameworks that we have, it kind of helps us to like quickly productionize from having just a model running on like a desktop to like having this run in a centralized location where everybody has access, visibility. There is logging, there's tracking, obviously with proper governance, and then exposing them for either for like batch inference or real-time inference. Cool. Thank you for coming. I really appreciate it. Yep. Thanks.